crouched in the bomb bay of a B-17F flying fortress, watching hydraulic fluid pool around his boots, while 20,000 feet below, the English Channel churned gray and hostile. The bomber had taken a direct hit from an 88mm shell over Wilhelmshaven. The nose section was gone. Everything forward of the radio compartment had been sheared away by German flak. 9 men aboard. 2 were dead. 7 were alive, but trapped 200 miles from home with no flight controls. The B-17F weighed 32,720 pounds empty. Fully loaded for combat, it reached 65,500 pounds. At 11:42, they were somewhere between those numbers. Fuel burning, bombs gone, but still heavy enough that without controls, the aircraft would enter an unrecoverable dive within minutes. Kowalski had been maintaining B-17s for 18 months. He knew every cable, every pulley, every hydraulic line in the flying fortress. He also knew that what he was looking at should have been impossible. The nose section housed the bombardier, navigator, forward gun positions, and most critically, the primary flight control cables that ran from the cockpit to the control surfaces. When the 88mm shell removed the nose, it should have severed those cables completely. The B-17 should have crashed immediately. Instead, Lieutenant Colonel James Morrison was somehow maintaining level flight from the pilot's seat. Morrison was fighting the aircraft with everything he had. The control yoke moved like it was connected to concrete blocks instead of control surfaces. Each input required both hands and maximum effort. His co-pilot, Lieutenant David Chen, was pulling on the yoke with him. Both men straining against controls that responded like they were moving through molasses. Morrison had radioed their situation to base control 15 minutes earlier. Nose section destroyed. Navigation equipment gone. Bombardier and navigator confirmed Kia. Primary flight controls damaged but functional. Hydraulic system compromised. Request emergency approach clearance at any available field. Base control had acknowledged but offered no solutions. There were no procedures for this situation. No training manual covered flying a B-17 with its nose shot off. Kowalski made his way forward through the radio compartment to where the nose section had been. The aircraft's aluminum skin was peeled back like an opened can. Wind blast at 180 miles per hour made movement dangerous. He clipped his safety line to the aircraft structure and crawled to the edge of the damage below. He could see the primary control cables. They had not been severed. Instead, the 88mm explosion had crushed the nose section around them, pinching the cables between twisted aluminum frames. The cables were still connected, but compressed under thousands of pounds of bent metal. The B-17's flight control system was mechanical. Steel cables ran from the cockpit controls through pulleys to the elevators, ailerons, and rudder. Cable tension was critical. Too loose and the controls would be sluggish. Too tight and they would bind or snap under load. Normal cable tension was 50 pounds. Kowalski estimated the current tension at over 200 pounds due to the crushed nose section. Morrison was essentially trying to fly the aircraft against the resistance of bent aluminum. Kowalski had two choices. He could try to cut away the damaged aluminum to free the cables. This would require cutting through structural elements while in flight, potentially weakening the aircraft to the point of structural failure. Or he could bypass the damaged section entirely by creating new control cable routes. This would require stripping cable from other aircraft systems and rigging connections in flight. Both options violated every maintenance regulation he knew. The intercom crackled with Morrison's voice. Control response getting worse. Need solutions fast. Altitude 19,500 feet, heading 095. Airspeed 165. Fighting to maintain level flight. Chen added his own assessment. Right elevator responding at maybe 30%. Left elevator less. Aileron sluggish. Rudder functional but heavy. They had perhaps 20 minutes before control degradation made level flight impossible. Kowalski made his decision. He would create emergency control cables using wire from the aircraft's electrical system. The B-17 carried over 3,000 feet of electrical wiring. Most of it was 12-gauge copper, strong enough to handle control loads if properly rigged. The plan was simple in concept, complex in execution. Run new cables from the cockpit to the control surfaces, bypassing the damaged nose section entirely. He started with the elevator system. The elevators controlled pitch. Without them, the aircraft would either climb until it stalled or dive until it crashed. Kowalski traced the existing elevator cables from the cockpit to the tail. The primary routing ran through the nose section and was compromised. He would need to create a new route through the aircraft's interior, running cables along the bomb bay ceiling to the tail section. The B-17's bomb bay was 13 feet long, 6 feet wide, 5 feet high. The bay doors were closed, but the space was still subjected to extreme wind pressure through various openings. Kowalski stripped 100 feet of 12-gauge wire from the radio equipment bay. The wire was designed to carry electrical current, not mechanical loads, but it was the strongest material available. He began rigging the wire along the bomb bay ceiling, using existing cable clamps and fabricated attachment points. The work required precision under impossible conditions. The aircraft was still flying at 180 miles per hour at 19,000 feet. The temperature was -15 degrees Fahrenheit. Kowalski worked without gloves because he needed finger dexterity. His hands went numb within minutes. The wind noise made communication with the cockpit difficult. He had to shout into the intercom to be heard. Each wire connection had to be perfect. A single failed joint could mean loss of control and immediate death for all 7 survivors. Kowalski had learned wire splicing techniques during his pre-war apprenticeship at a Chicago electrical contractor. Those skills developed for building wiring were now being applied to aircraft flight controls at 19,000 feet over hostile territory. He used a twist and solder technique, wrapping each joint with electrical tape salvaged from the radio compartment. The B-17's electrical system used different wire gauges for different applications. 12-gauge for high current circuits, 14-gauge for moderate loads, 16-gauge for low power systems. Kowalski was stripping 12-gauge wire, the heaviest available, but even this was marginal for control cable loads. Normal elevator cables were 3/32 inch steel wire rope with a breaking strength of 920 pounds. The 12-gauge copper wire had a breaking strength of approximately 180 pounds. He would need multiple parallel runs to achieve adequate strength. The mathematics were brutal but simple. 6 parallel wire runs would provide theoretical strength of 1,080 pounds, exceeding normal cable specifications. But copper wire behaved differently under load than steel cable. It stretched more, creating lag in control response. It was also more susceptible to fatigue failure under cyclic loads. Kowalski compensated by pre-tensioning each wire run to minimize stretch and by using longer attachment points to distribute stress. Murphy, the radio operator, monitored German fighter frequencies while Kowalski worked. The Luftwaffe was active over the North Sea that morning. FW-190s from Jever Airfield had been scrambled to intercept damaged bombers returning from the Wilhelmshaven raid. At least 3 B-17s had been reported as stragglers. German ground controllers were directing fighters to intercept them before they reached the English coast. At 12:15, Morrison reported that elevator control had degraded further. The aircraft was beginning to oscillate in pitch, small climbs and dives that were getting more pronounced. Chen was using engine power to help control pitch attitude, increasing power to climb, reducing power to descend. It was working but burning fuel rapidly. They had perhaps 90 minutes of fuel remaining, not enough to reach England with their reduced airspeed. The oscillations were getting worse. The aircraft would shake itself apart if the elevator problem wasn't solved soon. The B-17's right, R-1820 Cyclone engines were producing 1,200 horsepower each at current altitude. Normal cruise power was 65%, approximately 780 horsepower per engine. Chen was varying power from 45% to 85% to control pitch, well outside normal operating parameters. Cylinder head temperatures were climbing toward redline. Oil pressure was fluctuating as the engines worked harder than designed. Engine failure would eliminate their ability to maintain altitude. Morrison's hands were cramping from fighting the controls. The control yoke required constant pressure to prevent the aircraft from entering an uncontrollable dive. His arms ached from the strain. Chen was helping by pulling on the yoke during the worst oscillations. But both pilots were exhausting themselves fighting damaged controls. Sweat dripped into Morrison's eyes despite the sub-zero temperatures at altitude. The aircraft's trim tabs, small auxiliary control surfaces that reduce control pressure, were also damaged. Normal procedure would be to trim the aircraft for level flight, reducing pilot workload. But the trim cables ran through the destroyed nose section along with the primary controls. Morrison was flying a 65,000-pound aircraft with no trim assistance and degraded primary controls. It was like trying to steer a truck with a rope instead of a steering wheel. Kowalski could hear the strain in Morrison's voice over the intercom. The pilot was fighting a losing battle against degrading controls and time. Each oscillation was more violent than the last. The aircraft would pitch up 200 feet, then dive 300 feet, then climb again. The pattern was accelerating. Chen reported that engine temperatures were climbing as he used power changes to control altitude. The Wright R-1820 engines were not designed for rapid throttle movements at high altitude. Behind them, Staff Sergeant Miguel Rodriguez monitored the other crew members. Ball turret gunner Private Danny Walsh had taken shrapnel in his left shoulder, but was conscious and mobile. Waist gunner Corporal Tony Ricci had a head wound that was bleeding but not life-threatening. Tail gunner Sergeant Bob Franklin was helping Kowalski by holding wire runs steady while connections were made. Radio operator Technical Sergeant Paul Murphy was trying to establish contact with air-sea rescue frequencies in case they had to ditch. The psychological pressure was immense. Everyone aboard understood their situation. They were flying a partially destroyed aircraft over hostile water with improvised controls. Normal procedures had failed completely. Their survival depended entirely on Kowalski's ability to create a functional control system, using materials never intended for that purpose. There was no backup plan. No alternative. This would work, or they would all die. Rodriguez began organizing the crew for potential ditching procedures. Life rafts were located and prepared for deployment. Emergency radio equipment was checked. Personal flotation devices were distributed. The crew understood that if Kowalski's repairs failed, they had perhaps 10 minutes before the aircraft became uncontrollable. Ditching in the North Sea in March meant survival time measured in minutes, not hours. Water temperature was approximately 45 degrees Fahrenheit. Franklin worked alongside Kowalski with steady hands and mechanical aptitude. The 19-year-old tail gunner from Detroit understood machinery. His father had worked the Ford assembly line, and Franklin had grown up around tools and mechanical systems. He instinctively understood what Kowalski was trying to accomplish, and could anticipate needed tools and materials. Their collaboration was essential to the complex installation. Walsh, despite his wounded shoulder, maintained watch through the waist gun positions. German fighters were still active in the area. A lone B-17 flying slowly at reduced altitude was an ideal target. The ball turret was inoperative due to hydraulic damage, but the waist guns remained functional. Walsh monitored the sky continuously, ready to call out threats. His shoulder throbbed, but adrenaline kept him alert. The installation process required precise coordination between multiple crew members. Kowalski would position cable runs. Franklin would hold them steady while connections were made. Rodriguez would test mechanical linkages to ensure proper movement. Murphy monitored radio frequencies for navigation information and threat updates. Each man understood his role in keeping the improvised repair on schedule. Kowalski finished the elevator bypass at 12:23. The new cable route ran from the cockpit, through the radio compartment, along the bomb bay ceiling, through the rear fuselage to the elevator control quadrant in the tail. Total length, 47 feet of electrical wire supporting control loads. It was never designed to handle. He had used 6 parallel wire runs to distribute the load. Each connection point was reinforced with cable clamps salvaged from other aircraft systems. The improvised system looked like nothing in any maintenance manual, but the engineering was sound. Before testing the system with the pilot, Kowalski performed ground checks. He manually operated the elevator control quadrant in the tail, while Franklin observed control surface movement from the waist gun position. The elevators moved smoothly through their full range of travel. No binding, no irregular movement. The wire runs showed proper tension without excessive stretch. The connections held firm under manual load testing. He tested the system by calling for small elevator inputs. Morrison moved the controls carefully, testing response. The difference was immediate and dramatic. The control yoke moved smoothly instead of fighting against bent aluminum. The aircraft stopped oscillating. Morrison could maintain level flight with normal control pressure. Chen reported that engine temperatures were stabilizing as power changes were no longer needed for altitude control. Morrison performed a series of graduated control tests. Small elevator inputs first, then progressively larger movements. The aircraft responded predictably to each input. Pitch control was restored to approximately 70% of normal authority. More importantly, the dangerous oscillations had stopped completely. The aircraft flew stable and level for the first time since the flak hit. Control response improved significantly. Morrison's voice carried relief for the first time since the hit. Elevator authority approximately 70% of normal. Much better than before. But we still need aileron and rudder improvement. The aircraft was flying straight and level without constant struggle. Morrison and Chen could maintain altitude and heading with normal control inputs instead of wrestling the yoke, but they still couldn't turn properly or maintain level flight in turbulence without full aileron authority. Kowalski moved to the aileron system next. The ailerons controlled roll. They were essential for turns and maintaining level flight in turbulence. The aileron cables were also routed through the destroyed nose section. He would need to create another bypass. This routing was more complex because aileron cables split into left and right circuits. He would need 2 separate bypasses, each with its own cable runs and connection points. The complexity was daunting. Normal aileron cables were precisely tensioned and routed through carefully designed pulley systems. The cables had to move in exact synchronization. Left aileron up meant right aileron down, with precise differential movement. Creating this with improvised electrical wire would require perfect tension balance between the 2 circuits. Too much tension on one side would cause the aircraft to roll uncontrollably. Murphy reported German fighter activity increasing. Radio intercepts indicated that Luftwaffe ground control was vectoring fighters toward stragglers from the Wilhelmshaven raid. At least 2 B-17s had been shot down over the North Sea. German pilots were specifically hunting damaged bombers that couldn't maintain formation speed or altitude. A lone B-17 at 19,000 feet would be an ideal target for interception. Franklin, the tail gunner, had become Kowalski's assistant. The young sergeant understood mechanical systems and could follow complex instructions while working in cramped spaces. Together, they began mapping the aileron cable routes. The left system was simpler, a direct run from cockpit to left-wing route. The right system crossed the aircraft centerline in the nose section, requiring a completely new routing path. Time pressure was mounting. They had been working for over an hour. Fuel consumption was higher than normal due to Chen's power management for pitch control. German fighters were active in their area. The improvised elevator system was holding, but aileron control was still compromised. They needed both systems functional for safe approach and landing. Morrison could maintain level flight, but he couldn't turn effectively or handle crosswinds. The left aileron cable ran from the cockpit through the nose to the left wing root. Then through the wing to the aileron. Kowalski could bypass the nose section by running new cable through the navigator's compartment directly to the wing root. He stripped another 50 feet of wire from the electrical system. The aircraft's interior lighting failed as he removed the circuits, but daylight through the missing nose section provided illumination. Emergency lighting remained functional on battery power. Working in the navigator's compartment was particularly difficult. This was where Lieutenant Thomas Bradley had died. His body had been moved to the waist section, but blood stains and equipment damage made the space cramped and hazardous. Kowalski had to route cables around damaged instruments and through twisted metal brackets. Each connection point had to be tested under load before proceeding to the next. The right aileron required a different approach. The cable routing crossed to the right side of the aircraft in the nose section. With the nose gone, Kowalski had to create an entirely new routing. He ran cable from the cockpit down through the radio compartment, under the floor panels, up through the bomb bay to the right wing route. The route was longer and required more attachment points. The installation was complicated by structural damage from the flak hit that had twisted floor panels and created sharp edges that could cut the improvised cables. At 12:47, Kowalski completed the aileron bypasses. Morrison tested the controls carefully. Left aileron responding normally. Right aileron at about 60% authority, still sluggish but functional. The aircraft rolled left and right on command. Morrison could now turn the aircraft properly instead of relying on rudder and engine power for directional changes. The difference was immediately apparent as Morrison performed gentle turns to test the system. The rudder system remained compromised but partially functional. The rudder cables ran lower in the fuselage and had not been completely severed by the nose section damage. Kowalski examined the routing and found that the cables were bent around twisted fuselage frames but still connected. Rather than bypass this system, he decided to try freeing the existing cables. The risk was that additional damage might sever the cables completely. Using a combination of leverage and careful cutting, Kowalski removed several bent aluminum brackets that were pinching the rudder cables. The work was dangerous because the brackets were structural elements. Removing them weakened the aircraft's frame. But the alternative was leaving the rudder partially disabled. At 13:08, he freed the last pinch point. Morrison tested rudder authority and reported normal response. All primary flight controls were now functional. With primary flight controls restored through emergency bypasses, Morrison faced a new problem: navigation. The navigator was dead, his equipment destroyed. The radio compass was damaged. They had no idea where they were over the English Channel or which direction led to the nearest friendly airfield. Fuel remaining was approximately 1 hour at current consumption rates. Without accurate navigation, they could fly in circles until fuel exhaustion. Chen remembered a navigation technique from training: dead reckoning using time, speed, and magnetic heading. They had been flying heading 095 for approximately 30 minutes since leaving the target area. At 165 miles per hour, that placed them roughly 80 miles east of the English coast. If they turned to heading 270 and maintained airspeed, they should intercept the English coastline. The technique was crude, but better than guessing. Morrison made the turn to due west. The aircraft responded normally to control inputs. The emergency cable system was holding under flight loads. Kowalski monitored the bypasses continuously, checking for signs of stretching or failure. The electrical wire was not designed for this application, but it was stronger than expected. The real test would come during landing when control loads peaked during approach and touchdown. At 13:35, they spotted the English coast, white cliffs of Dover rising from gray water. Morrison's navigation had been accurate. They were approximately 20 miles south of their home base at Basingbourn, with enough fuel to reach the field. Base Control had been monitoring their emergency frequency and cleared them for immediate approach to any runway. The approach presented new challenges. Landing a B-17 required precise control inputs during the final descent. Airspeed had to be maintained within narrow limits. The aircraft had to be aligned precisely with the runway. Any loss of control authority during this phase would result in a crash. Kowalski's emergency cables had not been tested under the high loads generated during landing configuration. Morrison lowered landing gear and flaps gradually, monitoring control response at each setting. The emergency cables stretched slightly under increased loads but held their positions. Control authority remained adequate for approach. At 13:51, Morrison began his final approach to Basingbourn. Airspeed 125 miles per hour. Descent rate 500 feet. Per M in Ute. Runway alignment good. The touchdown was firm but controlled. Morrison held the aircraft straight down the runway using rudder and differential braking. The emergency flight control system functioned throughout the landing roll. The B-17 came to a stop, 4,800 feet down the 6,000-foot runway. 7 men climbed out alive. 2 would be buried in England. Post-flight inspection revealed the extent of Kowalski's improvisation. He had used 340 feet of electrical wire to create emergency flight control cables. The routing bypassed the destroyed nose section through 3 different paths: elevator cables through the bomb bay, left aileron cables through the navigator's compartment, right aileron cables under the floor panels. The system had handled full flight loads, including landing for over 90 minutes of flight time. Boeing engineers examined the aircraft the following week. They were particularly interested in the emergency cable routing. The engineering team had never considered this type of field repair. The electrical wire had stretched under load, but had not failed. The attachment points, improvised from existing aircraft fittings, had held without structural damage to the airframe. Load testing revealed that Kowalski's parallel wire configuration had actually provided 85% of normal cable strength. The engineers documented every aspect of the improvised system. Cable routing diagrams were drawn. Load distribution calculations were performed. Failure analysis was conducted on wire samples. The data showed that electrical wire could serve as emergency flight control cables under specific conditions. The key factors were parallel runs for load distribution, proper attachment point spacing, and careful attention to cable tension balance. Based on this analysis, Boeing developed formal emergency procedures for similar situations. The procedures were distributed to all B-17 maintenance units by July 1943. Field modification kits were created containing pre-measured wire lengths, connection hardware, and detailed installation instructions. The kits were standard equipment on all heavy bomber bases by September 1943. The repair technique was incorporated into emergency procedures training for B-17 maintenance personnel. Field modification manuals were updated to include emergency cable bypasses using available aircraft wiring. The procedure required at least 1 experienced flight engineer and approximately 45 minutes of work time. It was not a preferred solution, but it was better than no solution. Training emphasized that the technique was only viable if primary cables were damaged, but not completely severed. Multiple variations of the technique were developed for different damage scenarios: complete nose section loss, partial control surface damage, hydraulic system failure with mechanical backup requirements. Each variation required different wire routing and installation procedures. The common element was using available electrical wire to create emergency mechanical connections between cockpit controls and aircraft control surfaces. Kowalski was awarded the Distinguished Flying Cross for his actions. The citation read, for extraordinary achievement while participating in aerial flight. Technical Sergeant Kowalski, under extremely hazardous conditions, improvised emergency flight controls that enabled a critically damaged aircraft to return safely to base, saving the lives of 7 aircrew members. The technique was used successfully in at least 12 other instances during the remainder of the war. B-17s with damaged flight control systems were able to return to base using emergency cable bypasses created by flight engineers. The success rate was approximately 75%. Some aircraft were too severely damaged for the technique to be effective. But in cases where primary cables were damaged but not severed, the bypasses provided adequate control authority for safe return flights. Each successful application refined the technique further. Field engineers discovered that certain wire types worked better than others. 12. Gauge-stranded copper provided the best strength to weight ratio. Solid wire was prone to fatigue failure under cyclic loads. Multi-strand wire distributed stress more evenly and was less likely to fail catastrophically. These lessons were incorporated into updated field modification procedures. The psychological impact was as important as the technical success. Bomber crews gained confidence knowing that catastrophic control damage was not necessarily fatal. Flight engineers were trained and equipped to attempt emergency repairs. Pilots learned to recognize when emergency bypasses were feasible and how to assist with their installation. The entire bomber force became more resilient through knowledge and preparation. Morrison and Chen both survived the war. Morrison flew 31 combat missions and returned to civilian flying as a commercial pilot with United Airlines. He flew DC-6S and later DC-8 on transcontinental routes. Chen completed 25 missions and became a flight instructor at Randolph Air Force Base in Texas. Both men credited Kowalski's improvisation with saving their lives. They maintained contact with him for decades after the war, meeting annually at Air Force reunions. The other survivors also had distinguished careers. Rodriguez became a career Air Force maintenance supervisor, retiring as a master sergeant in 1962. Walsh recovered from his wounds and completed 28 combat missions. Ricci was medically discharged due to his head injury, but recovered fully and worked as an aircraft mechanic for Boeing after the war. Franklin flew 35 missions and became a pilot himself, transitioning to fighters in the Pacific Theater. Kowalski remained in the Army Air Forces through 1946, then joined the newly formed U.S. Air Force. He served as a maintenance supervisor on various aircraft types, including the B-36, B-47, and early jet fighters. His experience with improvised repairs made him valuable during the rapid technological changes of the early Cold War period. He trained a generation of Air Force maintenance personnel in both standard procedures and emergency improvisation techniques. The B-17 that landed at Basingbourne with emergency controls was repaired and returned to service. The nose section was rebuilt using parts from other aircraft. The emergency cable system was removed and proper control cables were installed. The aircraft flew 23 additional combat missions before the end of the war. It survived to be scrapped in 1946, having completed 67 total combat sorties. Kowalski retired from the Air Force in 1965 as a Chief Master Sergeant. He had served 24 years, most of it maintaining the aircraft that carried American aircrews into combat. His improvised repair technique had been refined and formalized, but the basic principle remained the same. When standard procedures failed, experienced maintenance personnel could often find alternatives using available materials and thorough understanding of aircraft systems. The 15th of March incident demonstrated something important about both aircraft design and human adaptability. The B-17 was designed with redundant systems and robust structure that could survive massive damage. But more importantly, it was operated by crew members who understood their aircraft well enough to improvise solutions when standard systems failed. This combination of good design and skilled personnel saved countless lives throughout the war. Frank Kowalski died on the 12th of November 2003, at age 82. He was buried in Arlington National Cemetery with full military honors. His distinguished flying cross was donated to the National Museum of the U.S. Air Force at Wright Patterson Air Force Base in Ohio. The citation is displayed alongside other examples of aircrew heroism during World War II. The emergency flight control bypass technique is still taught to aircraft maintenance personnel today. Modern aircraft have more sophisticated systems, but the principle remains valid. When primary systems fail, alternatives can often be improvised using available materials and thorough knowledge of aircraft systems. Kowalski's legacy lives on in the training of every flight engineer who learns that sometimes the best solution is not in the manual. The B-17F that survived the 15th of March mission was scrapped in 1946 as part of post-war demobilization. Its aluminum was recycled into civilian aircraft, but the lessons learned from that desperate flight over the English Channel became part of aviation history. Emergency procedures developed from real-world experience, tested under life or death conditions, refined through subsequent applications. If this story moved you the way it moved us, hit that like button. Every like tells the algorithm to share these forgotten stories with more people. Hit subscribe if you haven't already. We're rescuing stories like this from dusty archives every single day. Real people, real courage, real ingenuity under impossible circumstances. Drop a comment and tell us where you are watching from. Are you from the United States, United Kingdom, Canada, Australia? Our community stretches around the world. You are not just viewers. You are part of keeping these memories alive. Tell us your location. Tell us if someone in your family served. Just let us know you are here. Thank you for watching, and thank you for helping make sure Frank Kowalski and the crew of that B-17 don't disappear into silence. These men faced death and found a way to live. They deserve to be remembered, and you are helping make that happen. Stories like this remind us that when everything goes wrong, human ingenuity and courage can still find a way that is worth remembering, that is worth sharing.